Hi, in this video we are going to discuss the ray tracing visualization of quadric surfaces and generally implicit surfaces. In fact, we studied all the aspects of the solution of this problem. Now we just gather information from different chapters of the course. First of all, let me summarize the basic steps of ray tracing, assuming that the surface is defined in an implicit form. Implicit surfaces have an equation f where we put the Cartesian coordinates x, y, z into some algebraic expression and make this algebraic expression equal to 0. Sometimes it's more convenient to replace x, y, z Cartesian coordinates by the position vectors of the point. The ray, on the other hand, is a half-line defined by the equation of the line, where S is the starting point of the line, also called the position vector of the line, and D is a direction vector. This inequality, limiting t for the positive values, makes the line a half-line, because we are interested only in those objects which are in front of us. Those points are visible from the camera that are first intersected by the ray shot at a given direction. So in order to solve the ray tracing problem, we have to consider those points that are solutions for the implicit equation and also solutions for the ray. So we take the points defined by the ray equation and substitute these points into the implicit equation of the surface. So this is going to be a typically nonlinear equation for unknown parameter t. Here we know everything else. Of course we know function f because that defines the surface. We know s, the starting point of the ray, and also d, the direction vector of the ray. So this is a one-variate nonlinear equation for unknown parameter t. Somehow this equation should be solved. It may have more than one parameter since typically it is a nonlinear equation. If there are more than one parameter, we must select that parameter which is positive, which is in front of the eye, and if there are more than one positive parameters, that parameter which has the smallest positive value, because the surface at that point will occlude other intersection points. If we could determine t as the solution of this nonlinear equation, this t can be substituted back to the ray equation, determining the point in vert coordinates which is visible by the ray. In order to compute reflected radiance, we also need the normal vector of the surface at that particular point. Generally, for implicit surfaces, the normal vector at a point can be obtained as the gradient of the implicit function. Let me remind you that we have proven this in the lecture entitled Geometric Modeling of Surfaces. So the critical point of the ray tracing solution for implicit surfaces is the determination of the roots of this nonlinear equation. There is no general analytic solution for arbitrary equations, but there are cases which are very easy to solve. And one particular example is the quadratic equation, because everybody can solve a quadratic equation. We have a family of implicit surfaces called quadrics that always lead to a quadratic equation when the ray surface intersection calculation is executed. Quadrics are very convenient for ray tracing. We also studied quadrics in surface modeling. The implicit equation of a quadrics contains the x, y, z Cartesian coordinates at most in quadratic form, which means that we can see terms like x square, xy, y square, also linear terms like x or y or z, or even constant term like q44, but we cannot see anything else like x cube or x square y or xyz, etc. These are excluded from quadrics. When the ray surface intersection problem is considered, we have to replace xyz Cartesian coordinates with the equation of the ray, defined by starting point S, in Cartesian coordinates sx, sy, sz, and of direction d, which is defined in Cartesian coordinates with dx, dy, dz. So substituting these into the Cartesian coordinates and rearranging terms, we can always express this equation as a quadratic equation for unknown parameter t. This equation needs to be solved, and we are interested in the minimal but positive solution. We studied quadrics in surface modeling, so we know that if we take the geometric definition of the sphere, ellipsoid, hyperboloid, paraboloid, these geometric definitions can always be translated to a quadratic equation. So all these geometric objects belong to the category of quadrics. We have seen specific examples of a special ellipsoid that is in the center of the coordinate system, and the axes of the ellipsoid are the axes of the coordinate system, or a specially placed and oriented paraboloid, hyperboloid, or elliptic cylinder, etc. All these objects are family members of quadrics. And I have to emphasize that the ellipsoid or paraboloid or anything else can be not only in this very special arrangement when the center of the ellipsoid is in the coordinate system, but this ellipsoid can be anywhere in our virtual world and may have any orientation. We can still express its implicit equation as a quadratic equation. So when it comes to ray-object intersection calculation, we have to take the equation of the ray and substitute into these quadratic forms. It's very elegant not to consider every special type separately, but solve all types of quadratic surfaces generally. This is possible if we recognize that these quadratic equations can be defined by a general quadratic formula when we take x, y, z Cartesian coordinates, extend them with a constant 1 value, and this 4-element row vector is multiplied by a 4 times 4 matrix Q, and then it is multiplied by a 4-element column vector of Cartesian coordinates x, y, z and constant 1. This is a so-called quadratic form, and when a row vector and the column vector are multiplied together, we always have a scalar value, and this scalar value must be equal to 0. This Q matrix shows up here, so in fact Q11 determines the scalar parameter of term x square, Q12 the scalar parameter of xy, Q21 the scalar parameter of yx, etc. Since xy and yx are the same, we can distribute their scalar parameters evenly, so we can always assume that this matrix Q is a symmetric matrix, which means that Q12 is equal to Q21, and it applies for all other parameters simultaneously. So we can conclude that an arbitrary quadratic surface or quadrics can be defined in this form, where Q is a symmetric 4 times 4 matrix. So let us solve the ray quadrics intersection problem, assuming the equation of this quadratic form, where Q is a 4 times 4 matrix, which is multiplied by a 4-element row vector and a 4-element column vector. So this is the implicit equation. we know the ray equation, S the starting point plus d times t, where d is the direction of the ray. So the ray equation is substituted into the equation of the quadrics. So R is replaced by S plus d times t, both here and here, and then we have an equation for unknown parameter t. First of all, let us regroup components from this four-element vector that depend on t and components that are independent of t. The component that depends on t is d times t and 0. The component that is independent of t is s and 1. Exploiting the distributivity of matrix multiplication, we can break parentheses and rearrange this quadratic form into the following expression. Since d times t and 0 times t is proportional to t, we can extract t, and t shows up as a scalar parameter of this quadratic form. Here it shows up twice because t was included on the left-hand side and on the right-hand side of this matrix Q. When S1 is combined with T0 times T, T shows up only once, and when S1 is combined with itself, there is no T in the expression, so this is going to be just a constant. Indeed, this is a quadratic equation for unknown parameter t. Let me emphasize that here I already exploited the fact that Q is a symmetric matrix, because if Q was not a symmetric matrix, it should be written as S1 multiplied by Q and then multiplied by D0 plus D0 multiplied by Q multiplied by S1. Here, instead of this sum, I used only the first expression multiplied by 2, which is valid only if Q is a symmetric matrix. We have the solution formula for quadratic equations that can be applied, and as the solution we may have two roots. We have to check whether these roots are positive, ignore all negative solutions, and if there are more than one positive solution, then we obtain the smaller one. This is going to be the solution of the ray quadrics intersection problem. Taking this t and substituting this t back to the ray equation, we have a point R star, which is the point that is visible by the ray. When the normal vector is calculated, we take the gradient of the quadrics. We know the algebraic representation of the quadrics, so we can compute its gradient, and the gradient will be this. The point extended with force coordinate 1 is put into a row vector, and that is multiplied by a 4 times 4 matrix. The result will be a 4-element row vector. We obtain just the first 3 elements of this 4-element row vector, and that is going to be the normal vector. We exploit again that Q is a symmetric matrix. So why is it true? So let's calculate the gradient of this quadratic form. The gradient means that we calculate the partial derivatives with respect to x, y, and z, and these 3 partial derivatives will form a 3-element vector, which is called the gradient of implicit function f. So let us calculate the partial derivative with respect to x. Here we have a product, because this vector depends on x and this vector also depends on x, while q is a constant, so it is just a scalar term independent of the derivation. According to the derivation of products, first we have to derivate the first component, keeping the second component as it was before, and then the two components exchange their roles and the two derivatives are added. So first let us calculate the derivative of this vector with respect to x. The derivative of x with respect to x is 1. The derivative of y with respect to x is 0. The derivative of z with respect to x is also 0. And the derivative of a constant with respect to x is 0. So from this 4-element vector, derivation makes 1, 0, 0, 0. And first, we do not touch the second vector that includes x. Then the two vectors exchange their roles, so we preserve x, y, z, 1 from the original formula and calculate the derivative of the second vector. Similarly, the derivative is 1, 0, 0, 0 and add these two terms. However, if Q is a symmetric matrix, instead of adding these terms, we can multiply any of the two terms by 2 because these two terms are equal. Okay, so this is the partial derivative with respect to x. So what is the partial derivative with respect to y? Of course, very similarly, the same expression, but instead of 2, 0, 0, 0, we will have 0, 2, 0, 0. And the derivative with respect to z is the same expression, but 0, 0, 2, 0. So that's why I said that when the gradient is needed that contains the partial derivatives with respect to x, y, and z, we have to obtain this 4-element vector and extract the first three components. We have already implemented a class called sphere that handles the ray-sphere intersection problem. If we want to introduce quadrics in our virtual world, we need a quadrics class. That is also a special class of the intersectable, which means that it implements the intersect function that is responsible for calculating the intersection between the quadrics and the ray, and also for the determination of the normal vector at the intersection point. As we have concluded, such intersection calculation always leads to a quadratic equation, so the a, b, c parameters of the quadratic equation can be obtained. This is nothing but the evaluation of these three quadratic forms. If a, b, c are available, we can use the solution formula for quadratic equations. First, we have to determine whether the discriminant is negative or not, because if the discriminant is negative, there is no real solution. So we return with the His structure. In the His structure, the ray parameter is initialized to -1, so it indicates that this ray doesn't intersect the quadrics because there is no solution in the quadrics ray intersection problem. Otherwise, the square root of the discriminant can be calculated, and we use the quadratic solution formula to get the two solutions T1 and T2. If both of them are negative, then the intersection is behind the starting point of the ray. The ray is just a half-line, so in fact there is no intersection with this half-line. There is only an intersection with the line that contains this half-line, but this is not valid, so we ignore it. When we solved the ray-sphere intersection problem, we exploited the fact that in this scheme, T1 was always smaller than T2. However, if we use a general algorithm to determine parameters A, B, C, this assumption may not be valid anymore. So from these two parameters, T1 and T2, we really select that parameter which is positive, and if we have two positive parameters, which is smallest. And this is going to be the ray parameter associated with the intersection. If this is available, we can substitute this parameter into the equation of the ray. So we have the position in vertical coordinates of the intersection and the normal vector is obtained as the gradient, as this formula. Again, I need to emphasize that the formula which we used for the sphere is not valid anymore, so indeed we have to use this gradient calculation. The material of the surface at the intersection point is just the material of the quadric surface itself, and we can return with this solution. So we are done.